In this problem, we have x times e to the x squared plus 5. So notice I have e to a power that's not just a regular x. So I'm going to make u that exponent, x squared plus 5. The derivative of x squared plus 5, du dx, is just going to be 2x. And I'll bring up the dx to get to u by itself. So du is going to be 2x dx. And now I'm ready to change my bounds. So the lower bound on the integral is a -1, and the upper bound is a +1. So I'm going to switch out -1 and +1 that are in terms of x with what they'll be in terms of u. So I'm going to plug in for x here and see what I get out for u. So u is going to be x squared plus 5. So -1 squared plus 5. -1 squared is 1 plus 5 is 6. There's my new lower bound. And then I'm going to do 1 squared plus 5 to figure out my new upper bound is also 6. So that's kind of strange that our lower bound and our upper bound in terms of u end up being the same number. That's something that typically doesn't happen, but in this one it does, and we'll see how that affects our answer. So we're taking the integral from 6 to 6. And the first thing we want to think about is what's happening to our u. This is, u is up in the exponent, so it's not u to a power, it is e raised to the u. So this whole thing becomes e to the u. We've subbed in for that portion, and then we want to make sure we have our perfect du. So if we look, we need a 2, an x, and a dx for du, and all we have is an x and a dx. So we're missing a 2, in other words, we have 1/2 of our perfect du. We have x dx instead of 2x dx. That's half of the du that we need. The other way of doing it is let's just put the 2 in there. If we put 2 in there, we would get 2x dx. We'd feel good about writing du because we know we have it. And then we just put a 1/2 outside so that we don't double the value of the integral. So either way, we get 1/2 the integral of e to the u du. Now I'm ready to integrate. This should be the easiest part. You should normally be able to add 1 and divide by it and raise it as your new power. But this one, this follows the rule of the antiderivative of e to the x. The antiderivative of e to the x was e to the x plus c, so the antiderivative of e to the u would be e to the u plus k. Or in this case, e to the u with an evaluation bar from 6 to 6. So we're going to do 1/2, and we're going to do plugging in our upper bound minus our lower bound. Fundamental theorem of calculus. Well, e to the 6 minus e to the 6, anything minus itself is going to be 0. So we're only doing 1/2 of 0, which is 0. Why does that make sense? Well, as soon as I saw that the bounds were the same, we were taking the integral from 6 to 6 in terms of u. And we want to remember we're estimating area, or net area / change. So net area here, the width from 6 to 6 is 0 times any height is going to be 0. So because we're only going from 6 to 6, the width is 0. If we thought about drawing a Riemann sum here, if we thought about drawing a box, the width of the box would be 0. It doesn't even matter what the height is. The area, or net area in this case, would just be 0. So that's what happens when your bounds are the same number. Your answer is always going to be 0, and you didn't even really have to do any of that extra work, but we did because that was the first time that we plugged in and saw that the values for u were exactly the same. So our width was 0, and our answer was going to be 0 for the net area.